Hello everyone. In this lecture, we will be discussing about solution to a recurrence relation. We have already stated that a recurrence relation can be of two types, a linear recurrence relation and a nonlinear recurrence relation. We shall be restricting ourselves only towards the solution of linear recurrence relations. And for this, let us first try and understand what do we really mean by the solution to a linear recurrence relation. An example has been chosen where it has been stated that a linear recurrence relation an is equal to an minus 1 plus an minus 2 is given, together with its initial condition a0 equal to 1 and a1 equals to 0 and a1 equal to 1. We are supposed to find the value of a6. Now, in order to find the value of a6 from the given recurrence relation, if we try to put n equal to 6 in the left hand side of the recurrence relation, then we will get a6 is equal to a6 minus 1, that is a5, plus a6 minus 2, that is a4. So let us start from this. A6 is equal to a5 plus a4. Now we do not really know what the explicit value of a5 is and what the explicit value of a4 is. So in order to find the value of a6, we again have to find what is a5 and what is a4 by using the given recurrence relation itself. So if we put a5 is equal to a4 plus a3 and a4 is equal to a3 plus a2 from the given recurrence relation itself, then it could be simplified as a4 plus twice a3 plus a2. Now again, please look carefully that we do not know what is a4, what is a3 and what is a2. So we will be using the given recurrence relation again to find the value of a4, find the value of a3 and find the value of a2 so that we can get the value of a6. Now a4 can be written as a3 plus a2, a3 can be written as a2 plus a1 and a2 can be written as a1 plus a0, and as a result this a4 plus twice a3 plus a2 is simplified as a3 plus thrice a2 plus thrice a1 plus a0. Now again the same problem. We know what is a0, which is given in the initial condition for the recurrence relation. We know what is a0, which again is given in the initial condition for the recurrence relation, but we do not really know what a3 and a2 is. So we have to substitute a2 and a3 again by using the given recurrence relation, and if we do so, then a3 can be written as a2 plus a1, a2 can be written as a1 plus a0, and as a result this a3 plus thrice a2 plus thrice a1 plus a0 is simplified as a2 plus 7a1 plus 4a0. Now in this equation also, we know what is a1, we know what is a0, but a2 is unknown. Moreover, a2 can again be found, or a2 can again be simplified by using the given recurrence relation as a2 is equal to a2 minus 1 plus a2 minus 2, that is a2 can be written as a1 plus a0, and if we do so, then the entire expression is written in terms of the initial conditions given to us, and as a result we get the value of a6 as 8. Now if anyone asks me to find the value of A138 by using this procedure itself, it can be easily observed that the procedure of finding a particular term of the sequence is time consuming. If we want to find the value of A138, we have to start writing this A138 as the sum of A137 and A136. Then again this A137 has to be decomposed as A136 plus A135. Again A136 has to be decomposed as A135 plus A134, and so on until and unless the entire expression is written only in terms of A0 and A1. One can easily observe that the amount of time that will be needed for finding the value of A138 using this procedure will really be on a very higher side. Now let us consider that the same problem is given to us, that is the recurrence relation an is equal to an minus 1 plus an minus 2 is given to us, together with the initial condition a0 equals to 0 and a1 equal to 1. But this time an explicit form of an involving simply a function of n only is given to us. It can be easily observed that this right hand side of the equation an, that is 1 by square root of n times 1 plus square root 5 by 2 whole to the power n and so on, is nothing but a function of n. So we call such an expression or such an equation as an explicit formula for the given recurrence relation, and the advantage of using such an explicit formula is, if now anyone asks me to find the value of A6 or even A138, I will simply consider this A6 to be a function of n, and as a result I shall substitute n equal to 6 in this right hand side. Similarly, if anyone asks me to find the value of A138, then also I will replace n equal to 138 in the right hand side of this equation. And it can be easily observed that the amount of time taken to find A6 or A138 will somewhat be similar, and as a consequence we'll be able to say that using some constant amount of time we can find the value of A6 and A138 both. Now such an explicit formula to represent the nth term of a given sequence from the recurrence relation is known as the solution to the recurrence relation. We call this kind of a formula, we call this kind of an explicit formula as the solution to a given recurrence relation. So if we want to define formally, we can say that an explicit formula which satisfies the recurrence relation together with its initial condition is known as a solution to the recurrence relation. In the forthcoming lectures, we will be seeing how we can find the solution to a given recurrence relation which is linear in nature, and we will be discussing some related problems. So thank you for watching this one. Wait for the next one.